So welcome to our first recorded video on functions. Today we're going to talk about functions. We'll get our definitions, we'll look at some examples, and a couple of different ways to think about functions. Then we'll talk about properties of functions. The one-to-one property and the onto properties are both important. So let's get started. I'm going to unpin me and pin the notes. I hope that's in decent focus. So here are our goals. It's day 22. For those of you, let's see if we can get a little bit better focus. There we go. That are in Tuesday, Thursday, and it's day 23. For those of you who are in Monday, Wednesday, uh, here are a list of the things we're going to discuss, including domain, codomain, and probably in high school, what is actually the codomain you may have called the range. So we'll get those sorted out. Arrow diagrams, images and inverse images. And I'm talking about set theoretic inverse images, F inverse of a subset C of the codomain. This doesn't mean that F has a functional inverse. Then we'll talk about properties, one-to-one and onto. So let's get started with our definition. Given non-empty sets X and Y, so I'll use a big X and a big Y with feet here so we can distinguish them from other symbols, and a subset F of X cross Y. So think about what that means. It means the elements of F are ordered pairs with the first coordinate coming from X and the second coordinate coming from Y. We say F is a function from X to Y, so that's what we're defining, and it's denoted by F colon X arrow toward Y. We reserve this notation for functions only. So F is a function from X to Y, denoted by F from X to Y, if two things happen. One, each element little x in set X is paired with at least one, so the at least one element Y in set Y is what's important. And two, each element little x in set big X is paired with at most one element. We'll call it little y in set Y. So when you put those two together, it means each element of the domain is paired with exactly one element of the codomain. So X comma Y would be the ordered pair. If you'd like to write it very formally, we can use our there exists and for all symbols, and I'll teach you a new symbol. So it says for all little x in set big X, there exists a unique, and unique is indicated with an exclamation point, Y in set big Y, such that the ordered pair X comma Y, that's little x comma little y, is an element of F. So F is a set of ordered pairs. So this there exists a unique is a new way to use our quantitative quantifiers. There exists a unique element. So a couple more things. We call the set X the domain of F. So let's write that down. So big X, we call big X the domain of F. You're probably familiar with that term. And Y, big Y, set Y, the codomain of F. You probably used to call that the range. But technically, the set that we're quote unquote shooting at is the codomain of F. We may not hit everything in Y, like not every element of Y might appear as a second coordinate. However, those elements of set Y that do appear as second coordinates are images of elements from the domain. That particular set is what we call their range. We'll define that formally shortly, but we also say, well, you are probably familiar with this notation. F of X is equal to Y if, in fact, that ordered pair little x comma little y is an element of the set F. Okay? So a lot of this should look familiar. Let's look at some examples, keeping in mind that a function has a central dominating defining theme, and that is that every element of the domain, big X, is paired with exactly one element of the codomain, Y. All right, so just keep that in mind. And let's look at some examples and some non-examples because they can be just as informative. Examples and non-examples. All right. So example 1, we're going to let set big X equal the set containing 1, 2, 3, and 4. And we'll let Y equal the set containing 1, 3, 5, 7, and 9. These should look familiar. A is F, which is going to be defined to equal the set containing 1, comma 1, that's the first ordered pair, 2, comma 3, 3, comma 3, 4, comma 5, a function from X to Y. So there are a couple of ways just visually to check this. So approach 1 to solve or answer this question would simply be to check that each X, talking about little x, in set big X pairs with exactly one element little y in the set big Y. So we can just take a look. So the elements of X are 1, 2, 3, and 4, and we're checking to make sure that each one of those pairs with, or we say maps to, because this is going to turn out to be a function, which is also called a mapping. Well, 1 maps to 1, 2 maps to 3, 3 goes to 3, 4 goes to 5. So we can say maps to or goes to. Okay, so just for your notes, we say 1 maps to 1 and 2 maps to 3, excuse me. I wanted to make this a little more interesting than that. 3 maps to 3 and 4 maps to 5. Well, that's the way we would read this. And in fact, the answer is yes, it's certainly a function because each domain element maps to exactly one codomain element. Notice 2 and 3 are both mapping to 3 as the codomain element of Y, but that's okay. There's nothing that prevents elements of X from mapping to the same element in the codomain. There's no problem with that. And the other approach, we'll call this approach number 2, it gives us a different kind of visual, and it's the approach where we use an arrow diagram. And arrow diagrams make it really easy for us to see what's going on, and they'll be particularly useful shortly when we talk about the properties of a function. But here we go. We'll draw set X. It's got the elements 1, 2, 3, and 4, and I'll put the dots here on the right side so that I can write the numbers, which are the element names, on the left side, so my arrows won't get in my own way. And then here's set Y. It's got 1, 3, 5, 7, and 9 in it. And then we simply draw an arrow from the element of domain X to its partner, its second coordinate, over in codomain Y. So X is the domain and Y is the codomain in this game. Okay. So here we go. 1 maps to 1, so we just draw an arrow from 1 to 1. Make sure that your arrow actually has, a head on it, because we need to point toward the element of the codomain. 2 maps to 3. 3 also maps to 3. 4 maps to 5. This is the arrow diagram for the function f. Okay. So your visual check that this is the arrow diagram of a function goes like this. Each element in domain X, I'm talking about big X, because it's the set that's the domain, has exactly one arrow from it pointing into codomain Y. These second coordinates in F, and if we go back and look at F and look at the second coordinates 1, 3, and 5, are definitely elements of the codomain Y. And that's all that we need to have happen for this to qualify as a function. Let's take a look at another example. This will turn out, of course, to be our non-example. We're going to let set X be the same set that contains 1, 2, 3, and 4. And Y is going to be the same set with 1, 3, 5, 7, and 9 in it. We're going to define G, which will be a subset of X cross Y, as follows. Let's just make sure this is in good focus. Yeah, it looks like it's in good focus. How do we define G? Well, let's let G equal the set of ordered pairs 1, 3, 1, 1, 2, 5, 3, 7, and 4, 9. Of course, the question is G a function from X to Y? If you've been paying attention, you are probably already answering that question. So let's just take a look. Our solution can be approached again 2 ways. So let's look at this from the ordered pair approach, and then we'll look at it from the arrow diagram approach. So the question is, from the ordered pair approach, does each X, talking about little x, in set big X pair with exactly one little y in set big Y? Of course, that's actually the question. And of course, the answer is a resounding no. which I'm sure you have already seen. 1 is paired with 3, and then 1 is also paired with 1. So both 1 comma 3 and 1 comma 1 are in G. So G is not a function. It wouldn't be a function even if Y was a different set, even if X was a bigger set. Um, G's not a function already, no matter what else happened. And approach 2, if we take a look at the arrow diagram for this subset of X cross Y, which is actually technically called a relation from X to Y, and we'll talk more about relations when we get into chapter 8, but a relation from X to Y is simply any subset of X cross Y, including all of X cross Y, which would be pretty far from being a function. But again, if we just take a peek at the arrow diagram, you can see exactly what goes wrong. What goes wrong is that we're going to have an element. All it takes is one bad apple to spoil the for all requirement, that for all little x in X, there exists exactly one element, little y in set Y, that pairs with X. That fails because look, we have an arrow from 1 to 1, but we also have an arrow from 1 to 3. And the existence of those two different arrows is what makes this go bad. We may not have two arrows coming from the same domain element. If we want to just be complete, 2 maps to 3, right? And that pen isn't very dark. 3 maps to 7, and 4 maps to 9. It is a subset of X cross Y. But this particular arrow diagram, G, or 4G, is certainly not a function because of this problem. So a do later would basically ask you to explore, we'll call it example 3, the other thing that can go wrong, and that would be if there are elements of the domain that don't get mapped anywhere. So you can keep that in mind as you answer the same question in this do later. We'll just use the same X and Y that we've been using so far. I don't need to rewrite those. You know what they are. And that's as in examples 1 and 2, okay? Let's let H, which is going to be a subset of X cross Y, be H equals the set of ordered pairs 1 comma 1, 2 comma 5, 4 comma 9. And if you draw the arrow diagram or simply ask, does each X in the set X pair with exactly one Y in the set Y, you might realize that the element 3 in X doesn't map anywhere. And of course, the question is H a function? And I think you know the answer from X to Y. Now, it could be a function from a restricted subset of X. If we trim X down, we could make H a function from a different set X, a trimmed or restricted X into Y. But as long as we don't have that ordered pair 3, the ordered pair with 3 as the first coordinate, we're not going to have a function. Okay? So I hope that that's clear. Let's talk about the range of a function, because again, probably in high school, you were calling the domain, and you were probably calling the codomain the range, but they're actually different concepts. So let's talk about the range of a function or of function f. And now I'm going to change it up from A to B, just so that you get used to the idea that we don't always have to call the domain X and the codomain Y. So here's our definition of the range. Given a function f, from A to B, so I am using the functional notation because this is a function, we define the range of f. That's what we're defining. Denoted by, there's a little shorthand, it's capital R N G of f. Sometimes you see parentheses around the f, as follows. Well, what is the range of f? Well, intuitively, folks, it's the elements in Y that actually get hit by an arrow. So let's write this down using mathematics. The range of f is equal to the set of Y in B, the codomain, such that, or for which, or with the property that there exists an X in A. And this just means at least one. There could be several. But there exists an X in A where the ordered pair X comma Y is an element of F. In other words, these are the Y's that actually appear as second coordinates if we view the function as a set of ordered pairs. If we view the function with an arrow diagram, these would be the elements, little y, over in the codomain that actually get hit by an arrow. So here's our intuition. The range of F is the set of codomain elements that appear as second coordinates. So it's only the y values that appear, not appears, that appear as second coordinates. In any ordered pair in F, i.e. now we'll just switch from the ordered pair point of view to the arrow diagram point of view, the codomain elements that get hit by an arrow. And I'll put hit in quotes because that's not exactly technically a math term, but I like it because it gives us a clear visual. It's the elements in the codomain that are the output for some input X if you view F as an input-output type black box. Let's look at an example. Well, let's let A be the set containing 1, 2, 3, 4, and 5, and B be the set containing the elements, and now these will be alphabet letters, lowercase, little a, little b, little c, little d, little e, and little f. And we're going to let the function f, so don't get this function f confused with this little element f in the codomain, if you will, is equal to the set of ordered pairs 1 comma a, 2 comma b, 3 comma c, 4 comma d, 5 comma d. So part A is f, a function from A to B. And I think that you can see that that is a yes because each element of the domain, namely 1, 2, 3, 4, and 5, appears exactly once as a first coordinate in an ordered pair in the function. Each one of those has exactly one partner second coordinate from B. So we can just write a little sentence to explain. Each x in A maps to, so this is a perfectly normal kind of language for functions. So each x in A maps to exactly 1 y in B. All right. Now let's find the range of f. Since we're going to play the range game, it doesn't make sense to try to find the range of a relation. It only makes sense, just any old subset of A cross B isn't necessarily a function. It only makes sense to ask this question of range if we're looking at an actual function. So what is the range of f? Well, let's look at the second coordinates. Let's look at the elements of B that actually do appear as second coordinates. And you can see that the range of f is the set containing little a, little b, little c, and little d. Okay? And why is that? It's because these are the elements of B that appear as second coordinates of some elements in F, or some element in F. Okay. Example 5. We're going to use the same A and the same B. So A has the elements 1, 2, 3, 4, and 5. B is going to have the elements little a, little b, little c, little d, little e, and little f. And G is going to be a subset of A cross B, where G is the set of ordered pairs 1 comma F, 2 comma F, 3 comma F, 4 comma F, 5 comma F. Is G a function from A to B? And if it is, let's find the range of G. Well, this kind of function, where every domain element maps to exactly the same codomain element, is called a constant function, like the function y equal 5. Every x on the x-axis maps to y equal 5, and it's just the horizontal line, y equal 5. So every element of the domain A maps to the same element, namely little f of B. So it's definitely a function because 1, 2, 3, 4, and 5 each appear exactly once as the first coordinate, and their second coordinates are elements of B, namely the element of B that is f. So when we say, yeah, that's a function, it's actually a constant function, and the range of any constant function will just be a singleton set. In this case, the range of G is the singleton set containing the element little f. So we're talking about subsets of the codomain, and those subsets get to be the range of a function if they constitute the set of all the second coordinates of a given function. Now let's talk about images and inverse images. This is a fun game. Images and inverse images. Right. So here we go. Set ourselves up to play the game. Given a function f, from A to B, and subsets. C is going to be a subset of A, and D a subset of B. We define the image of C, and we're talking about under the function f, denoted by f of C as f of C is equal to, well, we're thinking about a subset C, so it's a subset of the domain, so some of the domain elements may be in C, okay? And we're thinking about where f sends those elements. It's sort of like that part of the range of f that's the range because of the elements that are sitting in C, which is part of the domain. So it's the set of Y in B. So they are the codomain elements Y from codomain B, such that there does exist an element little x in this set C where f of x equals y. So basically, it's where the arrows point to when those arrows are coming out of the subset C. Now, the inverse image of D, because D is a subset of the codomain, so we're going to look backwards. The inverse image of D, so we would image of C, and the inverse image of D, again, it's under F, denoted by, hey, Rock, you can hear my dog clickety clack, F to the -1 of D. This doesn't mean F actually has a functional inverse. This is a set theoretic inverse. As, okay, so how do we define it as? We define F inverse of D to equal the set of elements X in A, such that F of X lands in D. In other words, is an element of D. So we're looking backwards to see which X's in A had their arrows point into the subset D. So let's look at example 4 revisited. So F was going from A to B, where A is the set containing 1, 2, 3, 4, and 5. And B is the set containing little a, little b, little c, little d, little e, and little f. And again, F, excusing that we have two F's, but this is an element, and this F is the function, is that set 1, comma A, 2, comma B, 3, comma C, 4, map to D, 5, map to D. So 4, comma D and 5, comma D. And we're going to let C be a subset of A. Let's let C be this set. C is going to equal the set containing 1 and 2. And we're going to let D be a subset of codomain B, be this set. D is going to be the set that just contains the element little d. And then let's go ahead for good measure. Let's define H, also a subset of B. Let's let H be this set. Oops. Couldn't decide which word that S was going to go with. We need that S to go with this, and the next S to go with set. H is the set that just contains the element little e. So let's find each set below. Well, we're going to find f of c. We're going to find f inverse of d. And then, just for good measure, we're going to look at F inverse of H. Okay. So we've got our definition. The image of C is going to be the elements Y and B for which there exists an X in C, where f of X equals Y. So C is the elements 1 and 2. So we're looking at the element 1 and the element 2, and we're asking, what are the Y's over in B that are hit by the X equal 1 or the X equal 2? Well, 1 mapped to A, 2 mapped to B. So the image of C is the set containing A and B, because 1 mapped to A and 2 and C mapped to B. So the answer here is that this is equal to F of the set containing 1 and 2, because that is C, and that, of course, is just the set containing little a and little b. And that's because F of 1 is A and F of 2 is B. So you're just looking to see, where did the elements in C go? Where did they map to? Now, to find F inverse of D, we're going to look backwards. And we're going to find the x's in A whose images, f of x, landed in D. Well, we're looking at F inverse of just the singleton set that just contains the element little d. And we want to look backwards and find the x's in A that hit elements in set D. In other words, the elements of A that mapped to little d, because that's all that's in set D. Well, let's just take a look. Which elements from the domain mapped to little d? Oh, 4 and 5. So this is the set containing 4 and 5. So images are going forward. So we're following the arrows into C. Inverse images are looking backwards. We're going backwards and finding elements in the domain that mapped to whatever the set D is. This is because F of 4 is D and F of 5 is D, and that's it. Nothing else mapped to little d. So that's it. If there was another element over in domain A that mapped to little d, we would include it as the inverse image of the set D. Finally, the set H is the element little e in the codomain B. So we're trying to find F inverse of H. In 3, we're looking backwards to see what elements mapped into H. In other words, we're looking for F inverse of just the singleton set E. So we're looking backwards from E, and we're asking what elements in the domain hit E with their arrow, little e. Well, does little e appear as a second coordinate in any of the ordered pairs? No. So this is the empty set. It's not nothing. There's a difference between nothing and the empty set. The empty set is something. It's the set. It's like the bag. There's nothing in it. And this is because no x in A maps to the element little e. So it's okay. You can get an empty inverse image. Could we get an empty image? No, because unless we're looking at the image of the empty subset of the domain, which we don't generally do because that's not very interesting. But if you have some elements in your set C, we know each of those elements has to go somewhere, has to map somewhere. So if C is not empty, its image cannot be empty. We can't have an element of C mapping nowhere. That's not a function. That's what our example 3 is supposed to show us in our do later. All right. Hang with me. Ah, yes. So this is going to be called page 5B because my numbering was a little off. But what I'd like to do is just show you a picture. And in fact, I'm just going to show you the picture. It's the same problem that we just did, all right? And it's the same answers, but it's helpful to see the picture. So this is F. F is going this way. And C is the subset of A that has 1 and 2 in it, okay? And D is the subset of B that just had little element D in it. And of course, H was the subset that just had element little e in it. And the picture's nice because F of C means, okay, look inside this subset C, look at those elements, and trace where the arrows went that are coming out of set C, this subset of A, and they hit A and B. So it gives a nice visual backup. Similarly, if we want to look at the inverse image of a subset like D of the codomain B, well, here's D, and we're tracing backwards. Two arrows mapped into set D because there were two elements, namely 4 and 5, that mapped into D. D is just a singleton set, but it doesn't have to be. We can look at the inverse image of a larger subset. Don't think that the inverse images are only inverse images of singleton sets. We could ask, what's the inverse image of the entire set B? Well, that would be the entire set A because everything in A maps into B. And here H doesn't have any arrows going into it, so its inverse image is the empty set. So this is just an extra page of notes. Now, let's talk about infinite functions because infinite functions are something that are different than our little finite examples. We've just been looking at a finite domain. If you have a finite domain, of course, uh, the function itself is finite because each domain element has exactly one ordered pair that it's associated with. So if you have a finite domain, you have a finite number of ordered pairs. So we're going to talk about common domains first and codomains when we play infinite function games. These are the most common sets for domain and codomains for functions that are infinite. And those will be familiar. The reals, that's a very common set that's used as a domain or a codomain. And of course, it's infinite, so it gives rise to an infinite function. Even if everything in the reals maps to 5, for example, even a constant function with a finite range is still an infinite function because we have an infinite number of different x coordinates. Z is a common set that's used for a domain or codomain that's infinite. And then R plus, just the positive reals, or Z plus, these are the sets that you'll often see being used. So let's go to example 5. And let's look at a very familiar function, I hope, for you. Let's let f from the reals to the reals be defined by f of x equals mx plus b, where m and b are real numbers. I hope that you recognize that this is the general formula for a linear function. It's the polynomial of degree 1. What do I mean, degree 1? The highest power of the indeterminate, the variable x, is 1, right? It's not a quadratic with an x squared. It's not a cubic with an x cubed. The highest power of x is 1. This is a linear function, all right? And in fact, m could be 0, in which case this term goes away, and we're just looking at f of x equals b. That's a constant function when m is 0. So let's have just a little discussion about linear functions, just as a little warm-up reminder. The graph of f when it's a linear function is a straight line. Remember? And I bet you remember what M and B are. Well, it's having slope M, so M is the slope, the rise over the run, and y-intercept B. So the y-intercept is where the graph intersects the y-axis or intercepts the y-axis. Of course, on the y-axis, the x value is 0 because you haven't gone left or right at all. So x is 0 anywhere on the y-axis. So this y-intercept being b simply means that the point 0, that's your x value, comma b, is an element of f. So that's where it crosses the y-axis at 0b. And the slope, of course, well, if the slope m is equal to 0, we're talking about a horizontal line. It doesn't rise or fall. If the slope is 0, it's just a constant function that's always at the value y equal b. If m is greater than 0, then the line, of course, rises. It's sloped up. And if m is less than 0, I hope you remember that the line is falling or sloped down as we read from, of course, left to right. So that's just a little warm-up. Sort of the interesting game happens in example 6, where we take this idea of a linear function that we're fairly familiar with, but we restrict the domain and say, I don't want to use R, I'd like to use Z for my domain and codomain. So let's let F from Z to Z be defined by f of x equals mx plus b. And here, because I want the output, the codomain, well, the range actually values, the actual outputs, to be integers. So here, we're going to make sure that m and b are integers. And if x is an integer, which it will be, because the domain is z, and m is an integer, and b is an integer, we know that f of x will be an integer because sums and products of integers are integers. So here's a particular example that might help you visualize this idea. Like, what's the difference? Well, the points lie on a line, but they're just discrete points with a lot of space in between them. So let's look at y equal 2x plus 1. It's just an example of one of these linear functions with the countable discrete set z as the domain and the codomain. So I'll just say 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So -1, -2, -3, -4, -5. And then 1, 2, 3, 4, 5. And -1, -2, -3, -4, -5. It's not perfect, but you get the idea. Right, so let's graph some points that are on 2x plus 1. When x is 0, of course, y is 1. So 0, 1 is the y-intercept, and we expect that 1 would be the y-intercept. It is, just like it would be, because these points are going to be on the line that we think of when we think of 2x plus 1. The slope is 2, y-intercept is 1, but it's just not going to be all of the points. It's just going to be those that we get when we plug in an integer for x. So when x is 1, of course, y is 3. There's the point 1, 3. Here's the point 0, 1. And then when x is 2, y is 5. So we have the point 2, 5. And we still have this idea of a slope. The rise is 2 over the run of 1, right? So the slope is still 2 if you connected all these dots. When x is -1, of course, y is -1. So -1 is on there. And -2, -3 is also a point on this graph. Negative. So you get the drift. These are the points on 2x plus 1 when the x's are restricted to just the integers. This will become an important kind of example when we start asking about properties. Let's do that now. Let's talk about properties of functions. The one-to-one and onto properties, not necessarily in that order. One-to-one and the onto properties. We are now in section 7.2. I'm going to take a pause. I'll be right back. So these properties of functions we'll be able to explore by looking at coordinates of the ordered pairs. We'll also be able to explore these properties by looking at arrow diagrams. And it's nice to have both options. So the definition for onto and one-to-one are as follows. Given a function f, and we'll just go ahead and stick with a and b, so I don't have to draw my little feet from a to b. So given a function f from a to b, we say 1. F is onto, and we're thinking about onto the set B. And I like to think of onto as like a, oops. I'm going to pause again because it looks like my phone is shutting down. Hang on. Okay, so you can still see me, but it looks like I'm frozen. Hang on. Okay, let's see if there's an echo. Doesn't sound like there is. So we're back. Let's get back to it. So we're talking about onto. I think of F being onto codomain B, sort of in the same spirit that a wall-to-wall carpet is onto the entire floor. A wall-to-wall carpet covers the floor completely, and that's what onto means. B gets completely covered up with arrows. Everything in B gets hit by an arrow if F is onto. So F is onto B. Sometimes we just say F is onto if every element, let's see, is this still black? Every element Y in B appears as the image of some X in A. In other words, B is the range of F. Everything in B actually appears as a second coordinate. So if we want to think that way, we can do that. But I actually prefer to think about arrow diagrams as a way to understand onto every Y in B gets hit by an arrow. So by at least one arrow. It could be that several arrows hit some elements, but every Y in B gets hit by at least one arrow. And 2, F is one-to-one. If, and here's the technical definition of one-to-one, it is an if-then definition, and it goes like this. F of x1 equaling F of x2 is enough to imply that x1 is actually the same element as x2. In other words, if x1 and x2 map to the same y value or codomain value, then in fact x1 and x2 are the very same value over in the domain. So if we want to think arrow diagrams for one-to-one, it's symmetric in some sense, and that is that no y in B gets hit with more than one arrow. It's okay that a y doesn't get hit by any arrow at all. The function could still be one-to-one, but no element in the codomain can be the image of two different values, x1 and x2. So let's look at some examples so that this becomes a little more clear. And we'll think about an infinite function that everybody in the room is certainly familiar with. And that's let's let f, and of course we don't have to use the letter f. We could be calling our function g or h or k, but usually definitions and examples often use f. So let's let f be a function from the reals to the reals, be the basic quadratic, f of x equals x squared. And let's discuss why this f of x equals x squared, is neither onto nor one-to-one. It helps to look at a picture. So if we graph this f, we know it's going to be the basic parabola that sits with its vertex at the origin. We've got two copies of the reals. Of course, the horizontal reals are the x coordinate and the vertical axis is our y coordinates. And the squaring function looks really flat between 0 and 1. And once we get to the point 1, 1, it starts to rise very quickly. And of course, it's symmetric about the y-axis. Let's see if I can draw it. That's not very good. Doesn't look quite right here because it needs to be really flat, close to 0. And that's because if you square 1/2, you get 1/4. If you square 1/4, you get 1/16. So it gets really flat in here, but it's not onto, well, let's just look at that first because that's sort of the easiest thing to look at. The codomain is this entire real y-axis. And if we look at y equal x squared, the y values, of course, are the values that the function attains. And do we ever get a negative y value when we square a real value x? Nope. All of the y values that sit below the x-axis are y values that x squared can never attain. So this is not onto the reals because none of the negative reals get hit by arrows. None of the negative reals appear as second coordinates. So when we view the reals, let's get rid of that pin, it's not working very well, as the codomain. So we're looking at this copy of the reals. No y less than 0 is the image. And that's the phrase that we might say of any x, the image of any x in the reals when we're thinking about the x from the domain, the copy of the reals that is the domain. So it's not onto because none of these y's ever get hit down below the x-axis. But it's also not one-to-one. Well, let's talk about why it's not one-to-one. You remember in high school when you learned about how the graph of a set of ordered pairs could be tested with a vertical line test to see if it's the graph of a function. That set of ordered pairs is a function if as you slide the vertical line across the reals as the domain, that vertical line would never touch the graph in 2 points. So there's a horizontal line test for 1-to-1. And if a horizontal line touches the graph in 2 or more points then that's not a 1-to-1 function. So for example, if we think about 1, 2, 3, 4. So let's let this be y equal 4, okay? Well, if we look at the horizontal line, y equal 4, there are 2 x values that achieve that y value of y equal 4, right? x1 equals -2 maps to 4, and x2 equals +2 also maps to 4. So f of x1 equals f of x2, and I'm looking at the negation of the definition of 1-to-1, and x1 is not equal to x2. So to argue that this function is not 1-to-1, we're just going to grab a couple of x values that map to the same y value. And then we're going to show that the negation of this definition of 1-to-1 is what is satisfied with our choices. So let's let x1 equal -2 and x2 equal +2. So let's notice that f of x1, which is f of -2, is equal to 4. And f of x2, which is f of 2, is also equal to 4. But x1 is not equal to x2 because -2 is not equal to 2. So we've got a failure of the horizontal line test with this nice classic function that's neither 1-to-1 nor onto. Now we can make this function onto if we restrict the codomain to just the reals that are positive or equal to 0. So if we subtract away the negative reals and only look at 0 or positive reals, that means we're not considering the negative y-axis as part of our codomain, then the function actually is onto. But if the reals as a whole are considered to be the codomain, then this function is not onto. Now let's just think about linear functions, which we understand fairly well, and let's talk about why a linear function is always 1-to-1. And that's going to be true whether we're using the reals as the domain and codomain or the integers. So let's look at example 8. And we're actually on page 8, isn't that convenient? So functions that are linear. So we're looking at infinite functions first, and then we'll look at finite functions. But functions that are linear, i.e. it est, of the form f of x equals mx plus b, are always 1-to-1. So in our proof, if we just go back and consider the definition of 1-to-1, and it's an if-then definition, that f of x1 equaling f of x2 is sufficient to force x1 to equal x2. We just keep that in mind. We can prove that this if-then is true with a direct proof. We'll just assume f of x1 equals f of x2, assume the hypothesis, right? Because this is just an if p then q. So if we assume p, we'll be able to prove that q follows just by doing some basic math. We're going to assume m isn't 0 because we're going to have to divide by m. But watch this. Let's let f of x, oops, I just want to say f. Let's let f from the reals to the reals be defined by, and we could just call this A and B because it'll still work as long as we've got a field, because we need additive and multiplicative inverses. So we need a field, but so we'll just say reals to the reals be defined by f of x equals mx plus b, where m and b are real, and we want m to not be 0. So we can't play this game with a horizontal line. And let's suppose that x1 and x2 are in the domain, the reals, and also assume that f of x1 equals f of x2. So we're going to assume the hypothesis of the definition of one-to-one. We wish to show that x1 equals x2. Again, we can play this with any sets A and B that are real or just fields. So what does it mean that f of x1 equals f of x2? Well, this is f of x. Let's just put in x1 and let's put in x2 and let's set them equal to each other. So mx1 plus b is going to equal mx2 plus b. mx1 plus b is f of x1. mx2 plus b is f of x2. Because we have a field, so again, we can use any set that's a field. We can subtract b from both sides, and we get that mx1 is equal to mx2. And now we have to have multiplicative inverses or reciprocals. We can just divide both sides by m, and that's why we need m to not be 0. And the m's go away. That's perfectly legal, right? And we get that x1 is equal to x2. So any linear function is going to be a one-to-one function, because if f of x1 equals f of x2, we could easily prove that x1 equals x2. Now, it turns out that you can prove this same proof using a restricted domain. So even if we're using that the domain for x is z, and that m and b are integers, so that the codomain is also z, we can still perform these operations, because just because m is in z doesn't mean that we can only perform integer operations. We can allow ourselves to perform the operations in the larger set, which is the reals. I don't want to get too deep into those weeds, but let's just look at a non-example of onto. Now, a linear function from z to z is onto. You can always solve, and we'll show that in a minute, for an x. If you pick a y from the reals, you can always back up and find an x that will hit that y. In other words, every y in the reals will get hit by at least one arrow. In fact, it's exactly one arrow from the reals. But if we look at the restricted function, f from z to z, let's look at our little example. Let's let it be f of x equals 2x plus 1. We saw the graph of that a few minutes ago with just the dots. This is as earlier. Notice f is not onto. It's one-to-one, but it's not onto. It's not onto z. Well, let's think about it. When we plug in any integer x into the equation 2x plus 1, what kind of integer is going to be the function value or the output value? Those y's are odd numbers. They're of the form 2 times an integer plus 1. Those are only odd. So just remember or notice that 2x plus 1 is always odd when x is an integer. So no even integer in Z, which we're thinking of Z as the codomain, can be hit by an arrow coming from the domain. Because remember, there was space in between those. So if we go back and look at our picture of 2x plus 1, remember our picture here? Notice that the values that are the y values are like 1, 3, 5, -1, -3, -5 would be the next y value when x is -3. But none of the even integers on the y-axis are second coordinates. You can never get 2 or 4 or 0 or -2 or -4 as a second coordinate because this function only outputs odd numbers. So you can't hit every integer in the codomain set, which of course is Z, on the Y value. So linear functions are always one-to-one, but if we restrict the domain and the codomain to Z, not necessarily onto. Now let's just look at example 8 again and understand that sometimes these functions are onto. So functions that are linear. So I'm talking about functions that look like f of x equal mx plus b are sometimes onto. All right, so let's just look at the example when we are using the reals as the domain and codomain. So for example, we're going to let f from the reals to the reals be f of x equal mx plus b, where m and b are real, and m is not 0. So here's our proof. The claim is f is onto the reals. So the proof of the claim goes like this. We want to show every y in the codomain, which is the reals, gets hit by an arrow. In other words, is the image of some domain value. So let's let y be an element of the reals where we're thinking about the codomain, this copy of R. What do we wish to show? Well, we wish to show that there exists an x in the reals where we're thinking about the domain such that f of x equals y. We want to find something that's going to map to the arbitrary y. Well, if we just do a little scratch work in our head and we go over here and say, okay, y equals mx plus b, I want to find the x that's going to hit the y, you just solve for the x, and as long as m is not 0, x will be defined. So consider x equals y minus b over m. Clearly, x is real. Why? Because y, b, and m are real, and m is not 0. Now let's just show that this x will hit the y, which was the arbitrary y in the codomain that we grabbed. So f of x is f of y minus b over m. All right, so what does F do when it acts on y minus b over m? Well, F multiplies x by m and then adds b. So it's m times y minus b over m, because that's our x, plus b. Well, the m's cancel, and we're left with y minus b plus b, and of course then the minus b and plus b cancel, and we get y. So f, if we're talking about f from the reals to the reals, is onto the reals when we're thinking about the codomain. We hit everything in the codomain. We've already seen that if we restrict the domain of f to z and the codomain to z, then f is not going to be onto because we miss the odds. But if we go back and look at the one-to-one, let f from z to z be f of x equals 2x plus 1. The claim is f is one-to-one. It's the very same proof that we just saw for f from the reals to reals being one-to-one, because just because we're restricting x to the integers doesn't mean that we can't play games like divide by 2. We're not saying that we're not living in the bigger field. 2x1 plus 1 equals 2x2 plus 1 in our proof, where x1 and x2 are integers. So let x1 and x2 be in z, and we'll set f of x1 equal to f of x2. So we'll assume that f of x1 equals f of x2. And then it's just the same proof. Subtract b, and we get 2x1 equals 2x2. Divide by 2, x1 equals x2. So f of x1 equaling f of x2 still implies x1 equals x2. So f is one-to-one. Again, just because x1 and x2 are integers doesn't keep us from playing field games with the coefficient 2. All right, let's take a look at some finite examples of functions with respect to this idea of one-to-one and onto, because these are really nice. So a finite look at one-to-one and onto, because we can look at the arrow diagrams and really get a nice intuition for these ideas of one-to-one and onto. So here's our example 10 on page 10. How convenient. Let's let A be the set containing, why not, 1, 2, 3, 4, and 5, just like we did before. And B be the set containing little a, little b, little c, little d, little e, and little f. And f is going to be a function from a to b, where f is the set of ordered pairs. 1 maps to A, 2 maps to B, 3 maps to C, 4 maps to D, and 5 maps to D. This is the same example we looked at earlier, but now we're prepared to ask and answer these questions about one-to-one and onto. Is F onto? Does every element in the codomain get hit by an arrow? Is F one-to-one? Is it true that no element of the codomain B gets hit by more than one arrow? So in our solution, we're going to use arrow diagrams. And we can just redraw very quickly the arrow diagram for this particular, or did we actually ever even draw this one? I don't think we did. We've got 1, 2, 3, 4, and 5 as our domain elements, right? And in our codomain, we've got A, B, C, D, E, and F, A, B, C, D, E, and F, A, C, D, E, and F. And we draw the arrows for each ordered pair. So 1 maps to A. So we've got an arrow from 1 to A, 2 maps to B, 3 maps to C, 4 maps to D, and 5 maps to D. Okay, so that's our function F. So let's actually solve B first. I don't know why, but I'm just feeling like looking at the one-to-one property. Do you see how 4 and 5 both map to D? So, no, it's not one-to-one. Why not? Well, let's let little x1 equal 4 and little x2 equal 5. And notice f of 4 is D, but that's equal to f of 5, right? But 4 is not equal to 5. In other words, we have f of x1 equaling f of x2, but, which is and, x1 is not equal to x2. So that means the negation of one-to-one is what's satisfied. Now let's take a look at the question about onto. Does every element in the codomain get hit by an arrow? It looks like I'm frozen again. I wonder what's going on. I wonder how long that's been going on. I've just been deep into it. So I'm just not even going to bother to try to fix that for now because my phone is just dying. So I'm just going to let my phone die there. And I'll log back in here. Oops, in a minute. Sorry about that. There we go. So it's not onto. So in our solution to A, we simply have to find a y value from the codomain B that isn't in the range. In other words, the function is not onto if B is not the range or the range is not all of B. So no, it's not onto B because E is an element of B. And of course, you could also talk about F, but it suffices just to find one element of the codomain that's not in the range. E is an element of B, and E does not appear as a second coordinate of any ordered pair, i.e. NF, i.e. no arrow hits E, and E is in B. So one thing to ask yourself is, okay, in general, when the domain has 5 elements and the codomain has 6 elements, is it possible for us to build any function from A to B that is onto? So that could be our question C. Is it possible? Not just F, but could we build any function that's onto to construct a function H from A to B that is onto? Remember, here's some notation. The absolute value of A is equal to the number of elements in A. So it's a way to denote the size of a set. If it's a finite set, we could put the absolute value around it. So the answer is no, because the size of A is 5, but 5 is less than 6, and that's the size of B. We don't have enough arrows to cover up B, because we get one arrow from every domain element. We only get one arrow. We just don't have enough arrows, no matter where we send the elements of A. We just can't cover up B because B's got more points, more elements than A. We don't have enough arrows to quote unquote cover up the set B. So whenever we're looking at finite sets or sets that have different cardinality, and that means they're different sizes. If the domain is smaller than the codomain, it's simply impossible to build an onto function. Now, is it possible to build a one-to-one function? This function that we built here is not one-to-one because both 4 and 5 map to the same codomain element. But it is possible to spread the arrows out and build a function that is one-to-one. Just don't send any of these domain elements to the same codomain element as other domain elements. So it's possible to build a one-to-one function when the size of the domain is smaller than the size of the codomain. But it's not possible to build an onto function if the domain is smaller than the codomain. And if you want to think about it in the other direction, you can think about building functions from B to A, and you can ask yourself questions like, is it possible to build a function from B, which has 6 elements, to A that is onto? Sure, we have plenty of arrows. We have 6 arrows from any function mapping out of B, and that's more than enough arrows to cover up A. But is it possible to build a one-to-one function from B to A? Nope, because we have too many arrows in B. At least 2 elements are going to have to hit or have their arrows hit the same element in A. So you cannot build a one-to-one function from B to A because B is larger than A, but you can build an onto function. If A and B had the same size, you can build a function that is both one-to-one and onto. And that's the topic for our next lecture to complete our lecture series for Chapter 7. And that topic is the idea of functions that are both one-to-one and onto. What does that give us? What does that mean? It's going to mean that the function has what we call a functional inverse, where the inverse image set is actually a function itself. So there are some extra notes posted. So I just want to show you the extra notes, and they came from fall 24. And it just is a redescription of another way to think about one-to-one and onto, and another example, it's a different numbering, so it's a different set of notes where we've got an X and a Y, and it's sort of similar to what we just talked about with our A and our B. X has 5 elements, Y has 6. Is it possible to construct a function f from X to Y that's onto? If so, do it. Construct such an f. That means give me the ordered pairs. If not, explain why not. And is it possible to construct a function G from X to Y that's one-to-one? If so, construct such a function G, but if you can't, explain why not. And the other 2 questions that go along with this are in the last page of the extra notes. Is it possible to construct a function H that goes from Y back to X that's onto? If so, do it. If you can't, explain why not. And is it possible to construct a function k from y to x that is 1 to 1? If so, construct such a function k. If not, explain why not. And here are a complete set of solutions to those 4 questions. And you can read these at your leisure. And we will pick this back up. I'm going to just do this. And there we go. Get in focus. And thanks for playing. I'll post the second video as soon as possible. Have a great night.